Welcome to Cloud Wizard. In this video, we're doing a complete deep dive into the real-time bidding system, the infrastructure that decides which ad you see in the next 100 milliseconds every time a web page or app loads. We'll cover how platforms like Google AdX, The Trade Desk, and AppNexus run programmatic auctions using OpenRTB, how DSPs and SSPs interact, how bid prices are computed, and how the entire system stays under the 100 millisecond SLA at millions of requests per second. Whether you're preparing for a senior engineering interview or you're building programmatic ad infrastructure, this one is for you. Let's get into it. Welcome to Cloud Wizard. In this video, we are doing a complete deep dive into real-time bidding, the system that decides which ad you see in the next 100 milliseconds every time you load a web page or open a mobile app. RTB is one of the most latency-sensitive distributed systems ever built at internet scale. If you have ever wondered how Google AdX, The Trade Desk, or AppNexus run programmatic auctions, how DSPs submit bids in under 100 milliseconds, how SSPs maximize publisher revenue, or how OpenRTB defines the protocol that ties it all together, this video is for you. We will walk through the functional requirements, non-functional requirements, high-level architecture, the end-to-end user journey of a single ad impression, core models and auction logic, low-level design, and the trade-offs that come up in a senior system design interview. Whether you are preparing for a FANG interview at a company with an ad platform or you are actually building programmatic infrastructure, let's get into it. Here is the core problem. A user opens a news website. The publisher's page sends a bid request to an ad exchange within milliseconds. The ad exchange fans that request out to dozens or hundreds of demand-side platforms simultaneously. Every DSP must evaluate the impression, look up the user's targeting profile, run a pricing model, and return a bid or a no bid in under 100 milliseconds end-to-end, including network round trips. The winning bid is selected, the winning DSP is notified, and the ad creative is returned and rendered before the user even notices. Miss the deadline and your bid is treated as a no bid. Bid too high and you waste advertiser budget. Bid too low and you lose the impression. Scale this to trillions of ad auctions per day across desktop, mobile, and connected TV, and you have one of the hardest real-time distributed systems problems in the industry. This is the design challenge we are solving today. Let's walk through the functional requirements. First, the system must receive bid requests from publishers via supply-side platforms and ad exchanges using the OpenRTB protocol, carrying impression details, user signals, and floor prices. Second, a demand-side platform must evaluate each bid request, apply targeting rules based on geography, device type, audience segment, frequency caps, and campaign budget, and decide whether to bid and at what price. Third, the ad exchange must run a first price or second price auction among all received bids and select a winner. Fourth, the winning DSP must be notified with a win notice, and the winning creative must be returned to the publisher for rendering. Fifth, the system must support impression tracking, click tracking, and conversion tracking for measurement and billing. Sixth, it must handle no-bid responses gracefully and enforce bid timeouts with extreme precision. These 6 capabilities form the core of any production RTB system. Now the non-functional requirements. The single most critical SLA is bid response latency. The entire round trip from bid request to bid response must complete in under 100 milliseconds at the 99th percentile. That is P99 latency under 100 milliseconds. Throughput must support hundreds of thousands to millions of bid requests per second at peak, especially around live sports events or major retail moments. Availability must be 5 nines or better, because every second of downtime means lost revenue for both publishers and advertisers. The system must handle partial failures gracefully. If one DSP times out, the auction proceeds without it. User data must be handled in compliance with GDPR, CCPA, and TCF consent signals embedded in the bid request. The system must be horizontally scalable across multiple data centers and cloud regions to stay geographically close to publishers and reduce network latency. Budget enforcement must be accurate in near real time to avoid overspending campaign budgets. Here is the high-level system architecture. On the publisher side, A supply-side platform receives ad slot signals from the publisher's page or app and sends a bid request to the ad exchange. The ad exchange is the central orchestrator. It receives the OpenRTB bid request, fans it out to all eligible DSPs simultaneously via parallel HTTP calls, enforces the bid timeout, collects responses, and runs the auction. On the demand side, each DSP exposes a bidder endpoint. The bidder receives the request, queries a low-latency user data store for audience and frequency cap information, runs a bid price model, and returns a bid response. A budget pacing service tracks spend in near real-time using a distributed counter. A creative store holds ad creatives keyed by creative ID. After the auction, the ad exchange sends a win notice to the winning DSP, logs the auction for billing and analytics, and returns the winning creative to the SSP for rendering. A data pipeline asynchronously processes impression logs, click events, and conversion events for reporting. The key metrics to memorize cold. P99 bid response latency must be under 100 milliseconds. P95 is often under 50 milliseconds in well-engineered systems. Bid request throughput is measured in queries per second, or QPS, and top exchanges process millions of QPS at peak. Win rate is the fraction of auctions a DSP wins out of all auctions it participates in. Bid rate is the fraction of bid requests to which a DSP responds with a real bid, rather than a no bid. Fill rate on the SSP side is the fraction of ad slots that get filled with a paying ad. Cost per mil, or CPM, is the price paid per 1,000 impressions and is the primary billing unit. Budget utilization efficiency measures how closely actual spend tracks the intended pacing curve. Data freshness for user targeting data should be under 1 second for frequency cap counters and under a few minutes for audience segment membership. Let's trace the end-to-end journey of a single ad impression. A user loads a news article. The publisher's SSP JavaScript tag fires and sends a bid request to the ad exchange with the user's cookie ID, the ad slot dimensions, the floor price, and the OpenRTB payload including consent signals. The ad exchange receives the request, looks up which DSPs are eligible for this publisher and format, and fans the bid request out to all eligible DSPs in parallel, starting the 100 millisecond clock. Each DSP's bidder service receives the request, hashes the user ID to look up audience segments and frequency caps in a Redis cluster, runs a logistic regression or gradient-boosted model to predict click probability, multiplies by the advertiser's target CPC to compute a bid price, checks the campaign budget via a pacing service, and returns a bid response with the price and creative ID. The ad exchange collects all responses received before the deadline, drops late responses, runs a second price auction, selects the winner, sends a win notice to the winning DSP, decrements the budget counter, and returns the winning creative. The SSP renders the ad. The DSP later receives impression, click, and conversion events for billing and optimization. The core models and algorithms. The auction engine implements either a first price auction, where the winner pays their exact bid, or a second price auction, where the winner pays 1 cent above the second highest bid, plus floor price enforcement. The bid price model in each DSP predicts the value of an impression, typically using a logistic regression over sparse features or a gradient-boosted tree trained on historical click and conversion data. Frequency capping uses a distributed counter keyed by user ID and campaign ID, stored in Redis with a TTL equal to the frequency cap window. Budget pacing uses a token bucket or a smooth pacing algorithm that spreads spend evenly across the day to avoid front-loading. User targeting matches incoming user signals against audience segment membership stored in a key value store preloaded from a data management platform. The key trade-off in the bid model is between latency and accuracy. A simpler model responds faster but leaves money on the table, while a more accurate deep learning model may exceed the latency budget. Now the low-level design deep dive. The bidder service is a stateless HTTP service written in a low-latency language, typically Go or C++, running behind a load balancer. It deserializes the OpenRTB JSON payload, fans lookups across Redis shards in parallel using pipelining, runs the bid model inference synchronously in memory using a preloaded model artifact, and serializes the response. The user data store is a Redis cluster with consistent hashing and read replicas. Frequency cap counters use Redis INCR with expire for atomic increment in TTL management. The budget pacing service maintains a distributed counter using Redis with a sliding window and periodically syncs to the billing database. The Ad Exchange enforces bit timeouts using a deadline-aware RPC framework with circuit breakers on each DSP connection. Auction results are written to Kafka for downstream billing and analytics processing. The Creative Store is a CDN-backed object store keyed by Creative ID. For targeting data freshness, a changed data capture pipeline stream segment updates from the DMP into the Redis user store within seconds. Key takeaways for your interview. First, RTB is fundamentally a latency-constrained fan-out problem. The Ad Exchange fans a single bid request to hundreds of DSPs and must collect and aggregate responses in under 100 milliseconds, which forces you to design for partial results and aggressive timeouts. Second, the bidder is a read-heavy, latency-critical service. All user data lookups must be in memory or sub-millisecond Redis, and the bid model must be preloaded and served synchronously. Third, budget pacing is a distributed rate-limiting problem. Mention token buckets, sliding windows, and the trade-off between accuracy and throughput. Fourth, the choice between first price and second price auction mechanics has significant business implications for both advertiser spend efficiency and publisher yield, so be ready to discuss both. Fifth, data privacy compliance is non-negotiable. OpenRTB bid requests carry TCF consent strings, and your system must propagate and honor them for GDPR and CCPA compliance. If you can walk through this system with these 5 points, you will demonstrate strong senior-level thinking on one of the hardest real-time system design problems in the industry. That's it for the real-time bidding system design. If this helped, please like and subscribe, and I'll see you in the next one at Cloud Wizard. And that's a wrap on the real-time bidding system design. We covered the full picture from OpenRTB bid requests and SSP fanout, through DSP bidder architecture, auction mechanics, budget pacing, frequency capping, and the low-level design of the bidder service and Ad Exchange pipeline. If this video helped you, please hit that subscribe button and the bell icon so you never miss a new system design video. Drop your questions in the comments below. I read every single one. See you in the next one at Cloud Wizard.